Hello. Today we're going to talk about the importance of mixing and comparing some lab and large-scale equipment, and specifically the use of the RC1 and various Mettler-Toledo products. This is really an excerpt from a short course, the Fundamentals of Scale-Up, which I give, and also the I-Control mixing guidelines provided by Mettler-Toledo. And my name is Ronaldo Machado. I have a small company, RM2 Technologies, where I teach short courses in scale-up, but I'm also a full-time employee of Air Products and Chemicals. There are numerous physical and chemical processes that interact during a manufacturing or a synthesis process in a stirred tank. Kinetics, we're all very familiar with, which is the rate at which chemical reactions occur. There's heat transfer, that's the rate at which we're removing heat from the exotherm or adding heat in an endotherm. We have thermodynamics. Also, we have phase mass transfer between the phases that can occur: solid liquid, liquid liquid, and gas liquid. We need mixing to create dispersion of these multiple phases, or perhaps to homogenize a single phase with a semi-batch feed. There also can be physical changes. All these various things are going on simultaneously in a stirred tank reactor. For effective scale-up, we need to understand how they interact. There are a number of critical time constants that characterize a synthesis process. For example, the kinetic rate constant, which we're all familiar with, units of 1/seconds. In addition, we have the gas-liquid mass transfer coefficient, the reaction circulation rate constant, which is the agitator pumping rate divided by the volume. We also have micromixing, which occurs at the scale of turbulence, and it's the diffusion divided by the micromixing length scale. There's also a residence time and a host of other mass transfer and liquid mass transfer time constants. The magnitude of these rate constants dictates scale-up strategy, problem diagnosis, and optimization. Critical is to scale up on one of those key variables. Scale-up is about balancing these very different process rates as they change with process size. Unfortunately, the process rates do not change uniformly with the volume or the equipment size, and very often they go in opposite directions. Therefore, for a good strategy in scale-up, it is best to use one key mixing variable as the basis for your scale-up. Agitation intensity and agitator equipment design can truly impact many of these fundamental rate processes. For example, blending and macro mixing are affected mostly by the impeller pumping rate. Mass transfer can really be affected by a number of things, including the pumping rate of the impeller and the power per unit volume, which really breaks up the phases. Heat transfer is often impacted by the impeller velocity and design, and kinetics and selectivity can be very much impacted by the location of feed tubes and the pumping that is associated near that feed tube, be it the power per unit volume or the flow rate. And finally, the phase dispersion of liquid-liquid phases or solid-liquid can depend very much on the power per unit volume, the kinetic energy associated with that power, and the shear rate of the impeller. Mechanical power input is vital in understanding scale-up processes. Fortunately, agitators can follow a universal curve. That universal curve is given by the power number versus the Reynolds number. The power number is the mechanical power input to the fluid by the impeller divided by the liquid density, the rotation rate cubed, and the diameter of the impeller to the fifth. The Reynolds number is a measure of the inertial force versus the viscous force in the system, and is given by rho nd squared divided by the viscosity of the solution. At very low Reynolds number, we have laminar flow, and there the power number is inverse to the Reynolds number, whereas at high Reynolds numbers, the power number is constant for that given system. Given these curves, these master curves, we are now able to calculate how much power is being added to the fluid. The AP01 500 ml reactor has a unique agitator design that gives it appropriate mixing capabilities for diverse chemical systems, from high viscosity laminar flow to low viscosity turbulent flow. This is done by using 3 pitch blade turbines in addition to some extended baffles. This allows the system to operate with very good mixing under diverse conditions. We have master curves for the AP01 500 ml reactor, and they were developed for both 1, 2, and 3 impellers. As you can see, these impellers conform to the standard performance of an impeller, where we have the power number inverse to the Reynolds number at the low Reynolds number region or laminar flow, and eventually become constant at the high Reynolds number. We can use this correlation for that lab reactor to evaluate the power drawn by the impeller and use that information for subsequent scale-up and communication to the scale-up engineers. In this example, we're going to calculate the power per unit volume in an APO1 vessel that is filled with isopropyl alcohol at 20 degrees C. There's 325 mLs of solution, and we have the appropriate density and viscosity for isopropanol. We first calculate the Reynolds number and determine that we're in a range that is turbulent at 7,775. Knowing that, we can plug this number into our correlation. We know that we have one impeller in solution. We put the data in. We know that the turbulent power number is 1.85, and following the calculation, we can actually find that the input of the power was 1.64 watts per liter. This now can be used as an important parameter as we begin to evaluate the performance of our lab process and compare it to the mixing capabilities of the larger scale equipment. Another very important mixing parameter is the macro mixing time constant. Agitation impacts the macro mixing, and it really describes the uniformity of the composition at really the reactor scale. One of the ways we can measure this, and we can get and correlate data, is use a simple temperature probe that's inside a small lab reactor where we provide heat. That heat then provides a local zone of high temperature which becomes dissipated when the agitator is turned on. If we look at the graph, we can see that we plot on a log scale delta T over delta T max for the experimental system shown. From this, we get a curve that we can determine the mixing time constant and the T95, or the time that the system achieves 90% uniformity. For this example, it took 37 seconds. This becomes the basis of forming correlations of the mixing time as a function of different parameters. We have developed macro mixing correlations for the APO1 reactor. In this plot, we see the T95 times the agitation rate as a normalized mixing time, and that is correlated with the Reynolds number. At very long Reynolds number and very low Reynolds number, we see a constant value. And in between, in the transition region, we have an equation that describes the performance, or the T95, as a function of Reynolds number, volume, and the number of impellers. This can now be used to make evaluations of the mixing time and compare it to the large-scale vessel. In this example, we're going to calculate how long it takes for a monomer to dissipate and become uniform, 9 to 95% uniformity, in a small lab reactor. The polymer solution has a viscosity of 500 millipascal seconds, and the density is 1,200 kilograms per meter cubed. First, we determine the overall Reynolds number. We find out that it's 23, it's laminar or transitional. From this, we use our correlation, and we know that we have two impellers, we have a volume of 270 mLs, and from this we can calculate a T95 of 41 seconds. This can now be compared to the reaction rate time or the scale-up vessel characteristics. And this is useful in identifying whether or not the reaction will occur before or after the mixing is complete. Another critical variable is gas-liquid mass transfer coefficients. Let's take a look at the example of the reactor setup. First of all, it is important to always use a baffle. In the video clip on the left, we see that there's a non-uniform distribution of solids, gas, and liquid. When we use a baffle, this creates a more homogeneous mixture where gas and solids can be evenly distributed within the reactor. Using a baffle is critical whenever you undertake multi-phase reactions. Gas mass transfer can be described as a rate process, and the rate at which gas is absorbed is equal to a rate constant called the mass transfer coefficient, or the KLA. That is a function of the agitation intensity and, for example, the gas flow, in this case hydrogen. The driving force is the difference between the saturation concentration and the actual bulk concentration. We can actually measure or estimate the mass transfer coefficient by conducting a simple experiment. We take a reactor at 0 RPMs, we pressurize the head, and then we turn the RPMs up to a high value, 1,000 in this case. As you can see from the graph, the pressure drops in the reactor as the gas is absorbed. This rate at which the pressure goes down is actually an indirect measurement of the mass transfer coefficient. Using the equation on this page, we can use that curve of pressure drop to evaluate two critical pieces of information: the hydrogen saturation concentration and the mass transfer coefficient. The data is plotted as delta P over delta P max on a log scale versus time to provide you with a linear plot. The slope of that line gives you the mass transfer coefficient. If you do this for a number of different systems, we get the correlation below, which shows the RPMs and the mass transfer coefficients for a methanol system with different levels of methanol. You can now use this to correlate the mass transfer coefficient of your lab reactor with the mass transfer coefficient of the large-scale vessel. Solid-liquid mixing is also critical, and the agitation intensity impacts the solid suspension. For example, what we really want to do in any solid-liquid reaction is to ensure that the solids are suspended off the bottom of the vessel. The measurement for that is called the NJS. That's the rotation rate at which the solids are just suspended. It is critical to operate to get maximum mass transfer and process performance by keeping the particles off the bottom of the vessel. We can measure this in a couple of ways. Visually, we can photograph the bottom and make a note, or we can do things like place electrodes at the bottom of a simple solution that has a slight electrical conductivity. By measuring the conductivity of those two electrodes as a function of rotation rate, we can determine when the solids are suspended and compare that to our visual observations. The classic Zweitering correlation can characterize the solid suspension. It's a simple equation that has lasted over many years and still is one of the standards in the industry. In this, we want to calculate the NJS, or the point of just suspension. The variables include the viscosity of the solution, gravitational constant, liquid density, impeller diameter, the weight solid fraction in the liquid, the particle density and the liquid density, and the overall particle size. A critical parameter, however, is the S constant. That constant is a function of the laboratory or the plant equipment and must be determined empirically. From the previous example where we measured the NJS, we can now reverse calculate the actual S parameter used for the Zweitering correlation. When we plug in all the appropriate variables, we can determine that the S constant for this particular reactor configuration is 5.7. This then allows us to calculate the various agitation intensities necessary for different types of solids or particles in the system. There are tables available in scale-up equipment for the S values for large-scale equipment that should be available from your equipment suppliers. Next, we'd like to calculate the agitation rate for a full-scale reactor based on some observations in the lab scale. We're going to assume that in this particular lab experiment, we really don't know the physical properties of our system. We don't know the viscosity or the particle size. However, we want to reproduce this particular experiment at the large scale. So in that clear lab vessel, where we already know the S value from a previous calibration, we adjust our agitation so that the solid process is just suspending the solids off the bottom. At that point, we've determined the NJS. The next is to calculate the NJS necessary for the full-scale plant. To scale up based upon the Zweitering correlation, we can now take the ratio of the NJS for the plant and the NJS for the lab. Assuming that we have the same physical properties of particle size and solution properties in the large and small scale, which is what we're striving for, we see that they actually cancel. And now the NJS for the plant depends only upon the diameter of the impeller and the S values for the plant and the lab. With the S values known and the diameters measured, we can now calculate the actual requirements for the plant. Let's take our data now. The lab reactor had an S value of 5.7, a diameter of 6 centimeters. The NJS of the lab system was determined visually from your lab experiments to be 325 RPMs. From a table, we determined that the plant reactor had an S value of 4.6 and had a diameter of 24 centimeters. we can now calculate the NJS for that plant reactor by simply plugging in the numbers. And we find out that the plant must operate at least 81 RPMs to achieve a similar mixing condition as the lab reactor. In addition to the NJS, we can use that to calculate the actual mass transfer coefficients of the solid to the liquid. In this formula, we can see from Dr. Pangakar that by simply having the NJS value and some physical properties of the fluid, we're able to calculate the mass transfer coefficient combined with the specific surface area that we can get from the simple equation shown. We can actually determine the overall mass transfer coefficient in this example. This can be used now to compare different scales to understand at what level of mixing we need to get to achieve mass transfer for things such as Grignard reactions or even in crystallizations. It is important to operate just above the NJS and usually not much more. There's no need to overstir solids, and often this leads to problems. The following video clips have been extracted from the iControl software, which you can use to determine the proper mixing conditions in your vessel. In the first, we see that we have one baffle, a pitch blade turbine at 300 RPMs. We know the S values from correlations provided by the Impeller software. In the second one, we have 300 RPMs with two pitch blades, and we see the difference of just having two impellers versus one. Immediately, we see improved suspension. For this particular example of two pitch blade turbines, the NJS, according to the correlations, should be 530 RPMs. And that becomes apparent when we look at the video clip at 600 RPMs. And we can see that no solids are sitting on the bottom for more than 1 second. Very fast chemical reactions in a homogeneous liquid can be one of the most problematic scale-ups that you can encounter. Typically, the reactions are so fast that locally high concentrations can cause problems in selectivity and conversion to the proper products. Normally, you know this is a problem when your yield or selectivity is sensitive to things like agitation rate or the feed point location at which you add your materials, or the feed rate for that matter. The reaction is proportional to the feed rate, and the rate declines rapidly is often an indication that the reaction is very fast. Generally speaking, there are three mixing length scales and time scales which we can use to describe the scale-up of these fast reactions. Micromixing occurs at the scale of turbulence. It occurs at the very smallest structure within the fluid and is a function of the viscosity, density, and power per unit volume. Mesomixing occurs when there's a plume of material that comes from the dip tube or the feed tube that you're using in your process. It's typically at the scale of the feed tube diameter, and it's usually a function of the feed tube location and feed rate. And this is called mesomixing. Macromixing really occurs in the overall bulk of the reactor, and this is the scale of the reactor and is usually a function of the feed rate and the impeller pumping. And this has to do with the overall dilution of the feed within the tank. One simple visualization for low viscosity materials that are operating in a turbulent regime, micromixing would appear as a plume of material very, very close to the tip of the impeller and wouldn't go much beyond the tip itself. In this case, the overall mixing is determined by the local power per unit volume. In mesomixing, the plume goes well beyond the tip of the feed tube and into the reactor itself. And in this condition, it's a function of the feed tube location as well as the impeller size, dimensions, and power per unit volume. In macromixing, it's a little bit simpler. And here, the material finds itself throughout the entire reactor. However, the composition may be slightly non-uniform. Different mixing mechanisms can be impacted very differently by feed rate, feed location, viscosity, or the number of feed points. Micromixing, for example, is a strong function of the feed tube location and the viscosity, and is generally scaled up by the power per unit volume. Mesomixing is a strong function of the feed tube location, the feed rate, as well as the number of feed points, and is given by a more complicated function as a rule of thumb, which is the number of feed points times the rotation rate to the fourth power and d cubed, which is the diameter of the impeller, divided by the feed rate. Macro mixing, if that is the functional controlling step of your process, is really only a function of the feed rate. The rule of thumb is to take the overall pumping rate of the impeller, nd cubed, and divide that by the overall feed rate. That should be a constant upon scale-up. To visualize what's actually happening in a fast reaction, we're going to add iodine as a semi-batch feed to an aqueous solution of thiosulfate and starch. The iodine solution is yellow. As iodine reacts with thiosulfate, it becomes a clear solution. However, iodine can also react with the starch to become a black solution. Eventually, the absorbed iodine and starch will react with the thiosulfate to become sulfate and become clear. Let's take a look at what happens when we change the feed point and look at the two video clips on the left-hand side. You will notice very quickly that the closer the feed point is to the impeller, the smaller is the black plume associated with the process. We can think of the black plume as the byproduct example. If we look at the two video clips on the right side, what we'll see that as we increase the RPM, the size of the black plume is tremendously decreased. This is because the circulation rate and the power per unit volume are increased tremendously at 800 RPMs. You'll also notice that the black plume is also smaller when we have the feed tube closer to the impeller. And this makes sense to us and is intuitively what we would expect. At a better mixing point, we actually disperse the material before we make the byproducts. From the video clips, we calculated how long the black starch iodine complex took to disappear when the feed was stopped. And we correlated that reaction time with the T95 from the previous correlations that we had for this particular reactor. And we can see that there's a reasonable correlation between the reaction time and the T95. And this would be expected for this particular reaction. So for very fast reactions, this is what we would expect to do for scale-up as a first pass rule. One is to try to match the lab and the plant power per unit volumes. What this will tell you then is that the micro-mixing regimes will be very similar. In addition, we need to adjust the feed rate so as not to overwhelm the impeller. And to do this, what we do is we keep the feed rate divided by the impeller pumping rate a constant, or the feed time times the agitation rate a constant. Now, normally at a large-scale vessel, you have to run at lower RPMs, and as a result, your feed time is normally increased to maintain similar mixing conditions. For multi-phase reactions, we'd like to match our mass transfer coefficients, and now that we have correlations for the lab scale, we can continue doing this. For solid liquids, to maintain similar mass transfer coefficients, and also to maintain similar suspension, we would like to keep the Nj and N over the Njs a constant as we scale the process up. For liquid-liquid systems, it's a bit more complicated. There you must match the power per unit volume, your T95, and often the tip speed of your impeller. And in closing, for some very practical advice, if your semi-batch process gives you some poor results, one of the most important things you can do is slow down your feed. What this does is allows the impeller mixing to catch up to the overall feed rate. It allows dilution to occur more effectively and hence reduce the hot spots and local high concentrations in your vessel. In addition, you can dilute your feed concentration. This has a similar effect as slowing down your feed rate. You can increase your mixing intensity if it's possible in your large-scale vessel. And finally, you can always lower the temperature so that you slow down the reaction rate compared to the overall mixing. And this is some basic practical advice that you can use. And I thank you very much for your time. It's been my pleasure to talk with you this afternoon, and I hope that you can use this information to your advantage. I have a short course which is much more comprehensive, and once again, remember that some of these guidelines are simple guidelines and rules of thumb. Real chemical systems and real reaction systems require much more intensive analysis, and you need to look at your process more carefully. I thank you very much.